Design of Chebyshev transformers. In the previous video, we have presented the basic properties of Chebyshev polynomial, and we have seen how we can use Chebyshev polynomial to represent an equal rebel values in the range from x equal -1 to 1 and greater than 1 for x. The value of the Chebyshev polynomial would be greater than unity. This property would be used here to design Chebyshev transformer with equal reflection ripples in the passband, and after the passband the reflection will be increased. Returning back to the theory of small reflections, if we have multi-section transformer in this form composed of n section transmission lines Z1, Z2, Z3 until Zn, each section has length equals lambda over 4 at the center frequency. So the value of theta is pi over 2. In this case, the reflection coefficient gamma, the total reflection coefficient gamma, would be gamma naught plus gamma 1 e to the power minus j theta, gamma 2 e to the power minus 4 j theta, until gamma n e to the power minus 2 j n theta, where gamma 1 is a reflection from the first transmission line to z naught, gamma 2 is a reflection from the transmission line 2 to transmission line 1, and so on. Gamma n in general is Zn plus 1 minus Zn over Zn plus 1 plus Zn. We are planning to design a multi-section transformer whose reflection coefficient as a function of theta equals Chebyshev polynomial. So in this case, the proposed reflection coefficient of this multi-section transformer would be equal to specific magnitude A multiplied by e to the power minus j n theta multiplied by Chebyshev polynomial of sec theta maximum multiplied by cosine theta, where theta maximum is the phase angle theta, which corresponds to the maximum allowable reflection coefficient. This representation can be simplified by assuming that the sections are symmetric. So gamma naught equal gamma m and gamma 1 equal gamma n minus 1, and so on. For the case of symmetric transformer, the reflection coefficient can be represented in terms of cosine n theta, cosine n minus 2 theta, cosine n minus 4 theta, and so on, as a series of cosine n minus small n or minus 2n theta. Here is the reflection coefficient in terms of, or the reflection coefficient represented as a series of cosine thetas. This would be equated by the Chebyshev polynomial Tn multiplied by sec theta m cosine theta. At the first, we say that the magnitude A corresponds to the maximum allowable reflection coefficient, because the reflection or the Chebyshev polynomial inside the range where sec theta maximum cosine theta is greater than unity and less than greater than minus unity and less than unity, the Chebyshev polynomial has a maximum magnitude unity, and e to the power minus j theta n has a maximum magnitude unity. So in this case, the maximum magnitude of the reflection coefficient in this case equals the maximum magnitude of A. And in the pass band, the maximum allowable reflection coefficient is gamma m. So simply, we can say that the magnitude of A equals the maximum allowable reflection coefficient, or the magnitude of maximum allowable reflection coefficient. So by taking this, we have obtained the first unknown A. The second unknown is theta maximum. What is the maximum value of theta which can be obtained for a transformer of order n? To do this, let us assume the frequency tends to 0, or in other words, the lengths of the sections L tends to 0. In both cases, the value of theta would be 0. If theta equals 0, the reflection coefficient in this case, it would be the reflection coefficient between the load and the feeding transmission line direct, because in this case, all the transmission line sections of the transformer are assumed to be of length 0. So in this case, we are connecting the load to the feeding transmission line directly. Gamma of theta equals 0 equals z load minus z naught over z load plus z naught. When theta equals 0, the reflection coefficient here, it would be A multiplied by e to the power 0, it would be unity, multiplied by Chebyshev polynomial Tn sec theta maximum, cosine 0 is unity. So we say that gamma naught is A multiplied by Chebyshev polynomial Tn sec theta maximum. Okay? And in this case, we can say that the value of A equals z load minus z naught over z load plus z naught multiplied by 1 over the Chebyshev polynomial Tn of sec theta maximum. But we already said that the value of A is gamma m. So we can replace this by the magnitude of maximum allowable reflection coefficient. In other words, we can say that the Chebyshev polynomial of order n of sec theta maximum equals 1 over gamma m multiplied by the magnitude of z load minus z naught over z load plus z naught. In general, this value would be greater than unity. So we are talking about cosine n cosine minus 1x. We are talking about the Chebyshev polynomial of order n of x for x greater than unity. We are talking about cosine n cosine minus 1x. So this actually means that cosine capital N cosine minus 1 sec theta maximum equals this value. In this way, we can say that sec theta maximum, or 1 over cosine theta maximum, equals cosine 1 over n cosine minus 1, this value 1 over gamma m multiplied by the magnitude z load minus z naught over z load plus z naught, which can be approximated. We have seen before that z load minus z naught over z load plus z naught can be approximated as half ln zl over z naught. So we can replace z load minus z naught over z load by z naught, but half ln z load over z naught. So we can say that sec theta maximum approximately equals cosine multiplied by 1 over n cosine minus 1, the magnitude of ln z load over z naught over 2 gamma maximum. For a specific value of gamma maximum or maximum allowable reflection coefficient and specific value for z load and specific value for z naught, we can determine the corresponding theta maximum. And if we obtain theta maximum, we can obtain the operating bandwidth of this Chebyshev polynomial. Alright? That's what we are seeing. The bandwidth of the Chebyshev polynomial, it can be obtained by solving this equation, or in other words, this 1 over cosine theta maximum. So we can say theta maximum is cosine minus 1, the reciprocal of this cosine. So cosine minus 1, 1 over cosine, 1 over n, cosine minus 1, ln zl over z naught over 2 gamma n. Once we obtain the value of theta maximum, we can obtain the fractional bandwidth of the corresponding Chebyshev transformer as delta f over f naught equals 2 minus 4 theta maximum over pi. Okay? Till now, we have determined the value of A and the value of theta maximum. The remaining part is what is the magnitude of the reflection coefficients of the corresponding transformer. To do this, we say that we are going to equate the reflection coefficient of the multi-section transformer, which can be presented as a series of cosine n theta, cosine n theta, cosine n minus 2 theta, and so on, by the corresponding terms of the Chebyshev polynomial. The Chebyshev polynomial, as we have seen in the previous video, can be presented in the form of series of cosine n theta. So T1 of 6 theta maximum cosine theta is 6 theta maximum cosine theta. T2 is 6 squared theta maximum multiplied by 1 plus cosine 2 theta minus 1. T3 is 6 cube theta maximum multiplied by cosine 3 theta plus 3 cosine theta minus 3 6 theta maximum cosine theta, and so on. So, for example, if we are planning to design a Chebyshev polynomial of order 4, for example, which is here is the term 4, we have gamma theta have gamma naught cosine 4 theta. Gamma naught cosine 4 theta multiplied by 2 would equal the magnitude A multiplied by sec to the power 4 theta m multiplied by cosine 4 theta. This means that the term cosine 4 theta here and the term cosine 4 theta here, here it would be 2 gamma naught, here it would be A multiplied by sec to the power 4 theta maximum. In other words, gamma naught in this case would be sec to the power 4 theta maximum multiplied by A over 2. Right? Once we obtain gamma naught, we can obtain Z1 because gamma naught is Z1 minus Z naught over Z1 plus Z naught. So we can obtain the value of Z1. Gamma 1, it would be multiplied by cosine n minus 2. We are assuming that we are talking about n capital equal 4. So n minus 2 is 2. 2 here correspond to this term and this term. So gamma 1 multiplied by 2 here would correspond to A multiplied by sec to the power 4 multiplied by 4 minus A multiplied by 4 multiplied by cosine 2 theta. Actually, 4 multiplied by sec to the power 2 theta maximum. So in this case, gamma 1 would equal 2A multiplied by sec to the power 4 minus 2A multiplied by sec to the power 2 theta maximum. This how to obtain gamma 1. Once we obtain gamma 1, it would be Z2 minus Z1 over Z2 plus Z1. And already we have obtained Z1 from gamma naught. So in this case, we can obtain Z2. The last term for the case T equal 4 or gamma of order 4, it would be gamma 2 multiplied by cosine 0 or free coefficient. The free coefficient in this case is A multiplied by sec to the power 4 theta maximum multiplied by 3 minus 4 sec to the power 2 theta m multiplied by 1 plus 1. These terms are the free from any theta. It would be multiplied by a and divided by 2. It would be gamma 2. Once we obtain gamma 2, we can obtain Z3, which is the third element. And gamma 4 is the reflection from Z load to Z3. In this way, we can obtain gamma n, which correspond to Zn plus 1 minus Zn over Zn plus Zn, which can be approximated as half ln Zn plus 1 to Zn. In this way, we can obtain recursive relations to obtain the reflection coefficients. Once we obtain gamma naught, we can obtain gamma 1. Once we obtain gamma 1, we obtain gamma 2, and so on. So we obtain Z1, Z2, Z3, and so on. This is how to design Chebyshev matching transform. Alright? Okay. In the following video, we are going to present an example for such a design. The reflection coefficient for different order of n for Chebyshev polynomial, for n equal 1, it will be the conventional quarter wave transformer. For n equal 2, it would look like this. For n equal 3, it would look like this. And for n equal 4, it would look like this. It can be noted here, in the pass band, the reflection coefficient is not flat or is not zero, as in the case of binomial transformer. It is not zero, it has some magnitude, but this magnitude has a maximum value. And the operating bandwidth in this case is increasing by increasing the number of sections. This actually is the same as in the case of binomial transform. So the main difference between binomial transformer and Chebyshev transformer, in binomial transformer, the reflection and the derivative of the reflection along the bandwidth is 0, but here the reflection in the bandwidth has a maximum magnitude which does not exceed this maximum magnitude. Okay, let us see in the next video how to design or numerical example for designing such Chebyshev transform. Okay.